Hello and welcome. Today we're going to start talking about balancing chemical equations. Let us consider a simple reaction. If you take propane and burn it in the air, you get carbon dioxide and water. Well, that's nice, but this is science. We don't want to know that you can get carbon dioxide and water by burning propane. We want to know how much carbon dioxide and water you can get from burning propane. We want amounts. And to do that, the first thing we're going to have to do is balance the equation. So we have to talk about the rules involved in balancing an equation. And it turns out there aren't, in fact, a whole lot of complicated rules for balancing equations. The first one, of course, is straightforward. It's the law of conservation of mass. And the law of conservation of mass says everything you start with has to go someplace. Everything you end up with has to come from someplace. So every atom you have in the reactants has to show up somewhere in the products. Every atom you have in the products has to show up somewhere in the reactants. The second rule involved in balancing an equation is the law of definite proportions. And what the law of definite proportions says is that a compound contains the elements in an exact fixed ratio. So what does that mean? Well, we have 3 carbon atoms on the left side of our equation, so we have to have 3 carbon atoms on the right side. And we could do that by sticking in a 3 underneath the carbon in the carbon dioxide. And the question is that going to work? And the obvious answer, of course, is no, you can't do that. Carbon dioxide includes 1 carbon and 2 oxygens. You can't balance the equation by changing the formula of the reactants or products. The compounds have whatever formula they have. If we're going to account for 3 carbon atoms, we can't do it by changing the formula of the carbon dioxide. So to balance our equation, we have to decide where to start. And the best place to start is to simply pick on the thing that has the largest number of atoms in it. And why would we want to pick on the thing that had the most atoms? You want to pick on the thing that has the most atoms because you're going to have to account for everything eventually. And if you start balancing the smaller molecules, then when you finally get to the big one, you are likely to find out that you simply have to change all the other numbers. So it makes sense to simply start out with whatever is going to count for the greatest number of atoms. Propane has the greatest number of atoms in it, so we start by putting a 1 in front of the propane. And that 3 gives us 3 carbon atoms, and they have to be going somewhere in the products. And the only place we have carbons in the products is in the carbon dioxide. And since we can't change the formula of the carbon dioxide to account for our 3 carbon atoms, we have to put a 3 in front of the carbon dioxide. The 1 propane also includes 8 hydrogens. And so we have to have 8 hydrogens somewhere in the products. And the only place we have hydrogens are in the waters. And so do we need 8 water molecules? And the answer is no. The water molecules each contain 2 hydrogens. So we don't need 8 water molecules to account for our 8 hydrogens. We only need 4 water molecules to account for our 8 hydrogens. And that leaves us the oxygen. And how many oxygens do we have? Well, we could put any number of oxygens on the left, that would be fine. But on the right side, we have 6 oxygens in the 3 carbon dioxides and 4 oxygens in the water, and so that altogether is 10 oxygen. So do we need to put a 10 on the left side? And the answer, of course, is no. Because again, the oxygen's already present as molecules. They're already there in pairs. And so to get our 10 oxygen, we don't need 10 molecules of oxygen. We only need 5 molecules of oxygen. And so, everybody has a number in front of it. As the last check, we have to go through and count the atom. On the left side, we have 3 carbon atoms in the propane. On the right side, we have 3 molecules of carbon dioxide as our 3 carbons. On the left, the propane has 8 hydrogen atoms. On the right, we have 4 molecules of water, each of which has 2 hydrogens for our 8. And finally, we have 10 oxygens on the left in our 5 molecules. On the right, we have 6 oxygens in the 3 carbon dioxides and 4 in the 4 water molecules, and so we have 10 on each side. So the equation is balanced. So let's look at a somewhat more complicated reaction. The reaction of barium hydroxide with phosphoric acid produces barium phosphate and water. And so where should we start? Well, clearly the barium phosphate contains the greatest number of atoms, so we should start there. And we put a 1 in front of the barium phosphate and see where that takes us. Putting a 1 in front of the barium phosphate means we have 3 bariums. They all have to be coming from the barium hydroxide, so we put a 3 in front of the barium hydroxide. The barium phosphate has 2 phosphates in it. We have phosphates present in the phosphoric acid, and so we have to put a 2 in front of the phosphoric acid. And this is something else to keep in mind when balancing equations. When you have complex ions on both sides of the equation, you should handle them as pieces, as one thing. Eventually, we're going to have to worry about the individual atoms in them, but when you're balancing equations and you have complex ions on both sides of the equation, you should just go ahead and balance them as pieces. And since we have phosphates on both sides of the equation, we should simply balance them as phosphates. So having balanced the 3 bariums on each side and balanced the 2 phosphates on each side, we now have to account for the hydrogens. In the barium hydroxide, there are 6 hydrogens, 2 in each of the barium hydroxides. There are 6 hydrogens in the 2 phosphoric acids. So altogether we have 12 hydrogens to account for. They all have to be going to the water molecules. And since each of the water molecules has 2 hydrogens in it, we only need 6 molecules of water to account for our 12 hydrogens. And so, everybody has a number in front of it. The last step is to simply count out the atoms. So, on the left we have 3 bariums, on the right we have 3 bariums. On the left we have 2 phosphorus, on the right we have 2 phosphorus. Yes, we handled them as complex ions when we were setting out to balance the equation. But when you do the final check, you do the elements one at a time and you account for all the atoms. So for the oxygens, there's 3 times 2 in the barium hydroxides. There's 2 times 4 in the 2 phosphates. That's a total of 14. On the right, we have 2 times 4 in the phosphates, and we have 6 in the water molecules. Is that 14? And finally, the hydrogens. Each of the barium phosphates has 2. There's 3 of them. Each of the phosphoric acids has 3. That's 6 more. And on the right, the 6 water molecules have 12 hydrogens. And so our equation is balanced. Organic compounds, which include nitrogen as well as carbons and hydrogens, are referred to as amines. Amines have a general chemical property. They smell terrible. That compound is trimethylamine. Trimethylamine is the smell of rotting fish, so it smells terrible. But like most organic compounds, it burns really nicely in the air. And in addition to producing carbon dioxide and water, it also produces molecular nitrogen. And so we need to start out and balance this equation. Clearly, starting with a 1 is not going to do us any good. We have 2 nitrogens in a molecule in the products. So starting out with a 1 in front of the trimethylamine is not going to do us any good. Which brings us to the next step of balancing an equation. When you know you're going to need several of something, don't start with a 1. Start with multiples when you know you're going to need multiples of something. 2 trimethylamines gets us 2 nitrogens. They go to form the molecule in the products. In addition, the 2 produce 6 carbons. Those all have to be going to the carbon dioxide, so we need 6 of those. They also include 18 hydrogens, and so those are going to the water molecules, but the water molecules has them in pairs, so we're only going to need 9 water molecules, which brings us finally to the oxygen. Well, the 6 carbon dioxides include 12 hydrogens. The 9 water molecules include 9 more. That's 21 oxygens. And so we need 10.5 molecules of oxygen. And is that going to work? And of course the answer is no. No, no, no fractions. You can't have fractions of atoms or molecules. If you have them, you have all of them. You can't have fractions. So no, you can't use fractions to balance the equation. Which means in this case that we have to back up and start over. We don't have to start with 2 of the trimethylamines, we're going to have to start with 4 of them. 4 nitrogens form 2 nitrogen molecules. 12 carbons present in the 4 trimethylamines go to form 12 carbon dioxides. 36 hydrogens in the 4 trimethylamines go to form 18 water molecules. And now, finally, we come back for the oxygens. The 12 carbon dioxides have 24 oxygens in them. The 18 water molecules have 18 more. That's 42 oxygen atoms we need. So we're going to have 21 molecules of oxygen. And are we done? Well, not quite. There's one more thing we need to go back and check. And that is, we need to make sure that we've not only balanced everything, but we've used the lowest possible numbers to do it. We want to have the lowest whole number ratio of the elements. So, 4, 12, 18, and 2 are all divisible by 2, but 21 is not. 21, 12, and 18 are all divisible by 3, but 2 and 4 are not. So yes, in fact, those are the lowest numbers that work. And so, in fact, we have come to the last step where we count up the individual atoms to make sure everything is balanced. And so those are the steps for balancing an equation. And that brings us to the end of today's discussion on balancing equations. Go have a nice day.